everyone, we are getting close to being done learning solving exponential and log equations type stuff. And what I want to do towards the end here is work on something that kind of pulls all the pieces together, and that is finding inverses of exponential functions and or log functions. So this first example, we start with an exponential function, and we're going to find its inverse. We're going to check ourselves by composing the function in its inverse. We're going to think about domain and range as we do that, and we're going to sketch the function in its inverse. So it makes us practice a whole bunch of the things that we've been doing with exponential and log. Okay, so if we want to find the inverse and we're given a formula, we switch our x and y. Our first step here, we're solving for y, will be to divide by 3. So we get x divided by 3 equals 2 to the y minus 1. We then need to get rid of the exponential base 2. So I will take a log base 2 of each side. And nothing too nice happens on the left-hand side, but on the right-hand side, the exponential and the log will cancel and we'll just have a y minus 1. So my last step will be to add 1 to both sides, and I'm going to go ahead and rewrite that down below as f inverse will be that log base 2 of x over 3 plus 1. So we just added 1 to both sides. And you cannot add that 1 inside the parentheses. Make sure you don't make that mistake. Just like this is great. This is our inverse function. So to find the inverse, we have to practice solving the exponential equation. Next, we will compose f of f inverse. So we want to plug our log base 2 of x over 3 plus 1 into our original function. And our original function will give us back 3 times 2 to the input that we just wrote down, and then that's minus 1 in the exponent. And then we're just hoping to see some things cancel out. We supposedly built a function that undoes everything the original function was doing. The first thing I notice is that those parentheses don't have any multiplication or exponents or functions attached, just a subtraction. So we can drop those off. There was nothing to distribute. And when I do that, it makes it easier to spot that the first thing to go will be the 1s. I have a plus 1 minus 1. So I'll get 3 times 2 to the log base 2 of x over 3. The next thing to go will be the exponential and the log. Just like if you have the log base 2 of 2 to the x, it cancels. The same thing happens when you have 2 to the log base 2 of x. So the 2 and the log base 2 are gone, and we're left with 3 times x over 3. And that x over 3 is not in the exponent anymore. That's what happens when the canceling is done. The x over 3 drops down. And then the last thing to go is we're multiplying by 3 and dividing by 3. So we just end up with x. And this one is interesting. We haven't had a lot, I don't think so far this quarter, where we had interesting domains, but here we do. So this will make us go back a little ways and review something. We have an original function whose domain was all real numbers, but our inverse function can only take x greater than 0. So basically x over 3 has to be greater than 0, but when you multiply both sides by 3, that means that x itself has to be greater than 0. So what we're looking at here when we talk about the domain of the composite function is back to that two-step thing that we haven't had to think about for a little bit. In order for input to survive a composite function, it first has to be a valid input for the inner function, and then the output that we get has to survive the outer function. So in this case, just to survive the inner function, we have to make sure that we start with an x greater than 0. The outer function is exponential, so it can take anything that we give it, so we're not going to lose anything on that step 2. So really here, if we check that inner domain, we should be in good shape and we shouldn't get into any trouble taking what we get from the log function and plugging it into the exponential. So this composition also has a domain x greater than 0. Now we want to compose the other direction. So we want to take our original function, hold on, I gotta peek, 3 times 2 to the x minus 1, and we want to plug it into our inverse. So the inverse function is a log base 2 of x, which is now getting replaced by 3 times 2 to the x minus 1, over 3 plus 1. So this time, the first thing to go is going to be the 3's. I'm multiplying by 3, I'm dividing by 3. That will cancel. This is what I'm left with. The next thing to go will be the log and the exponential. They're both base 2, so they cancel, and I'm left with an x minus 1 plus 1. Those parentheses I don't really need. I can just say that subtracting 1 and adding 1 will cancel each other out, and I'm left with an x. So once again, it is looking like I found an accurate inverse. This time when I think about the domain of the composite, I look at this inner function and it is exponential, so its domain is all real numbers. So to survive step 1, I don't have to worry about anything. No matter what I choose, it'll survive step 1. To survive step 2, I know I need to have, so the output has to be greater than 0 because whatever I plug into this log down below has to be greater than 0. It turns out, though, that with inverses, this is going to kind of work itself out automatically, but we can even think through it. We're talking about an exponential function. So if I'm thinking about the original function that I started with, it's a 2 to the x. It's been vertically stretched by 3, and it's been shifted right by 1, but none of that will affect the fact that we have a horizontal asymptote at y equals 0. And we go up from there. So we are getting numbers that are greater than 0 from our inner function, which means they'll all be okay for the outer function, which means the domain of the composite here is all real numbers. We will see this again with rational functions and radical functions, and it gets pretty interesting there, so we'll get into it even more. But I hope you're starting to catch that we need to check the inner function, and then we need to be a little thoughtful about what's happening with the outer function. But it is true that when you're composing inverses, that outer function step should usually be a safe one. So domain restrictions when you're composing inverses are going to come from that inner function. Last step here is just to sketch these two. So use this to practice your transformations. My original function was 3 times 2 to the x minus 1, and we just kind of talked about that one. But if I pick a couple of points, I'm going to follow the horizontal asymptote, and I'm going to follow the point 0, 1, and 1, 2. So when I do vertical stretch by 3, that doesn't move the horizontal asymptote. 0 times 3 is still 0. When I move to the right 1, that also doesn't affect the horizontal asymptote. So the exponential function will still have a horizontal asymptote at y equals 0. The point 0, 1, when we do vertical stretch, it goes to 0, 3. And then when we shift to the right 1, it goes to 1, 3. And then the point 1, 2, when we do stretch, it goes to 1, 6, and then when we shift to the right, it goes to 2, 6. So 2, 6. So my graph, and just because I'm interested, I'm going to go ahead and plug 0 in here. So if I plug in 0, I get 3 times 2 to the negative 1, which is 3 times 1 half. So it crosses at 3 halves. You don't have to have that right, but it always bugs me if my y-intercept is weird, so I just double checked it. So that is a pretty decent rough sketch of my exponential function. To get my log function, I can do the same sort of thing. I can say, okay, I'm starting with a log base 2. Let's see, what was my log function? It was y equals log base 2 of, x over 3 plus 1. Let me just double check. Yes. Okay. So log base 2 has a vertical asymptote at x equals 0. It crosses at 1, 0. And then we have another point at 2, 1. So this is my log shape. And then when I do my transformations, it's horizontal stretch by 3 and shift up 1. So x equals 0. When I do horizontal stretch, that won't move. 3 times 0 is still 0. And when I move up 1, it also won't move. So this is at x equals 0 still. If I take the point 1, 0 and do horizontal stretch, it ends up at 3, 0. And then if I shift up 1, it ends up at 3, 1. 2, 3, 1. And then the point 2, 1, when I do horizontal stretch, ends up at 6, 1. And then when I shift up, it ends up at 6, 2. So this is my sketch of the log function. You may have noticed that we saw some really similar things happening. It's just that they were happening to x's instead of y's or vice versa. And you may realize my axes aren't quite square, but I should get that reflection across y equals x because they're inverses. So I think you should practice the sketching by transformations because that tends to be something that people take a little while to get good at with exponential and log. But I also think you should note things like the exponential goes through 1, 3, and the log goes through 3, 1. If we didn't have that nice pair matchup, I'd be worried. The exponential went through 2, 6, and the log went through 6, 2. So it does look like we're getting inverses. And then we're asked about the domain and range. So for the function, the domain is all real numbers, and the range is y greater than 0. For the inverse, the domain is x greater than 0, and the range is all real numbers. And you should see that the domain and range switch. That should always happen for inverse functions. So these are really nice. I'll try not to have you do too many because it is time consuming, but these are really nice for putting all the pieces together. Thanks for watching.